So, good morning, everyone. And thanks for making the adjustment to be on here. Okay, so I'm taking attendance, and there's no real pattern to how people are placed in here. Let's see. Okay. That's everyone. Okay. So, today we're picking up where we left off, continuing to talk about finding limits algebraically. Like has been happening for people, I guess all of you, but especially for people remotely, the lecture notes are posted on Canvas. I'll be doing a little voiceover walkthrough of those. And I'll also be posting the video online. Okay, do one last check here. Right. So let's get to this. Okay. So to briefly recap what we've been doing and to highlight a good way to start organizing this information. Sorry, people coming in. Okay, so a way to organize this information for problems where on an exam, say, you'll be given a problem, here's a limit, what is it? And it won't necessarily have a graph with it, so it'll be a little tougher to decide what's going on, and there won't really be context with it. You'll have to figure out what tools do I use to figure out what is going on with this limit. And so far, our little flow chart, I guess, that we're coming up with is for rational functions like this one. This was the example we ended with last time. For rational functions, or even things with some square roots or fraction or different exponents in them, if you can, the first step is really take this number, -1 in this case, and put it into the function. If the bottom isn't 0, so if you're getting a number, then that number is the limit that you're looking for and you're done. Last time what we also talked about was if you put this number in and the bottom is 0 but the top isn't, that says you have a vertical asymptote and you have to figure out what's going on around that asymptote. And that was what a lot of class yesterday was talking about, or yesterday meaning last class. The example we ended with last time was that if you put in this case, you put in -1 into this function, both the top and bottom are 0. So this is an example of what's called an indeterminate form. Indeterminate because from this form, you just have no idea what's going on. There's nothing to really be gained other than you have to do some other work to figure out what's going on. In this example, the work was factor the top. You can, well, this is the actual work that you'd be reproducing, or that looks like what your solution would actually be. So you have this limit, it has this 0/0 form, you can factor the top, you can cancel them. This fact says if you have a function and where you're taking a limit, you can find the limit of the simplified version instead. So the limit you're looking for, do any simplifying and work with the simplified version. And this limit x minus 1, that's a polynomial. That's something we can find by putting in -1 and we get -2. To emphasize this indeterminateness, I want to pull up this graph. So we saw this last time, but I want to show you something a variation. Okay. So again, that function was x squared minus 1 divided by x plus 1. So this was the graph that we got, and as that work we did shows, the limit at x equals -1 is -2. It's not really showing up here, but there's a hole at -1 because, there's a hole at -1 because you can't put -1 into this function. But even if there's a hole, the graph heads down towards height -2. So if I take this function and I flip it upside down, so x plus 1 divided by x squared minus 1. So this is another indeterminate form. If you take the limit of this as you go to -1, if you put -1 into the top and bottom, you get 0 for both of them. So this is an indeterminate form, but if we graph this, we get very different behavior. Is this? Right, so this function, if you put in -1, right, it's 0/0, but the simplified version of this is 1/x minus 1. So these two functions are the same, and at -1, this is -1/2. So these two functions have the same 0/0 form, but they have really different behavior. So that's the indeterminateness. 0/0 tells you nothing about what's actually happening with the function. You have to do some extra work. As another example of this, I'm going to look at the following function. So a little drawback is it's hard to do a slow reveal of kind of things, but look at this limit right here. So this isn't rational. It has the square root, but it's still the kind of function where if we put in this point and get a number, that point is the limit. But what happens here is if you put in 0, well, the bottom is definitely 0. If you put 0 in the top, you get the square root of 4, that's 2. 2 minus 2 is 0. So this is another instance where our limit has this indeterminate form of 0 over 0. But unlike last time, we can't really factor the top. So for this limit, how it's similar is it's indeterminate, which means we have to do some algebra, and the eventual goal is to do some cancellation, find some factor on the top and bottom we can cancel, which allows us to find the limit of what's left after simplifying. What is kind of obviously very different is we can't factor the top, so we're going to have to do some really different algebra. For limits of this type, with this square root, there's a essentially correct move to make. There's one algebraic maneuver you can do, which will get you to a place where we can do the cancellation we're looking for. And this is what's called multiplying by the conjugate. So what I mean by conjugate is you look at this square root expression on the top, this square root minus 2. Take the version of this with a plus instead of a minus and multiply that on the top and bottom here. So we're allowed to do this because multiplying and dividing by the same thing is multiplying by 1, which doesn't change the function. So these are the same function. This just has more stuff. This is a really messy looking 1. But the reason for this is the algebra that happens when we try to multiply this out. So first, on the bottom, we don't do a lot with it. Just multiply them by writing them next to each other. X times this square root of x plus 4 plus 2. Just write it as x times the other denominator. On the top, though, what we're going to do is distribute this so we FOIL it out. And if we look at what happens when we multiply this out, so the square roots, multiply those together, the square roots cancel, like squaring the square root to get just x plus 4. This positive 2 times this square root doesn't simplify, but you have it there. This negative 2 times this square root, which we write there. And then the 2's multiply, since one of them's negative, we get negative 4. Then what we see, and this is why multiplying by the conjugate is the right thing to do, these two terms with the square root are exactly the same, except one of them's negative. And so we have 2 times this square root minus 2 times this square root. Those things cancel, and we don't have any square roots in the top at all. And what will happen is that, or what we can know is that this always happens. If you do this multiply by the conjugate move, the square roots will always cancel each other out. And we'll end up with no square roots at all on the top. Before we keep going, are there any questions about getting to this point, this multiplying by the conjugate and the kind of associated algebra that goes with it? So in dealing with the square root, we can't factor it. There's this other multiplied by the conjugate move, and the end result is we don't have any square roots on the top. But that's not where we stop, and maybe you thought when I got to here, you're saying, why are we stopping? There's some really easy stuff that we can see to do. So in particular, you have this 4 minus 4. The parentheses, which were kind of left over from here, we don't need them. So we can cancel the 4 and minus 4 to get just an x. And then this is what we were looking for. There's an x on the top and an x on the bottom. And what we really wanted was to be able to cancel those. So just like in the rational function example that's up, what we wanted to do was find some cancellation, because as soon as we do that cancellation, we can take the limit of what's left by evaluating. And if we look at what's left, with those x's gone, the top is 1, the bottom is the square root of x plus 4 plus another 2. This is the kind of limit where we can put in 0 and get a number out. And what happens here that makes this work is, because there's a plus and not a minus, the bottom isn't going to be 0. If you look at the minus version, which showed up in our original limit, we had the square root minus 2. If you put in 0, that turned out to be 0. In the positive version, they add instead of subtract, so we don't get 0. And we can finish this out. If we put in 0, 1 over the square root of 0 plus 4 plus 2. This is the square root of 4. That's 2. 2 plus 2 is 4. So this limit that we're looking for is 1/4. Questions about this problem? Either any steps in here or kind of how this compares to the other problem that the other indeterminate form cancellation problem that's the top half of this page. So a kind of broad takeaway is, if you encounter these indeterminate forms, what you know needs to happen is you need to do some algebra, which eventually leads to some cancellation, and you can find the limit of the canceled version, what's left after the cancellation. But how you get to that cancellation, and then you can take the limit after that step, is kind of dependent on what function you have. If you have a square root, this multiplied by the conjugate process is really the way to go. If it's a rational function without the square root, you can try to just factor it and find the cancellation value. So the next thing that I want to talk about is piecewise functions. As the example we'll start with, the absolute value function. This is a piecewise function that says if you input a number greater than or equal to 0, just output that x. If you input a negative number, output minus x. So it always gives us things greater than or equal to 0. In particular, in this case, if you put in a negative, you give it another negative sign, and that becomes positive. And it has this familiar V-shape graph. So we'll use this as our example piecewise function, but the way that we approach piecewise functions, there are really two cases. One is you're at a point where you switch from one piece to the other piece. So here, that would be 0. 0 is the point in the middle where you go from using x to using minus x. But also, you might want to find a limit not at a switching point. And that second case is actually the easier one. So for instance, if you want to say, take the limit as x goes to 3 of the absolute value of x. A little less stuff. If you want to find the limit as x goes to 3, well, 3 is well inside this. It's not at a switching point. Graphically, you can think of this as saying 3 is over here, and it's not, so around 3, we're always using x. Around 0, we're using both pieces, but around 3, we're only using the x piece. So how we proceed is we're saying if we want the limit as x goes to 3 of this absolute value of x. Well, since around 3, we're always using this piece x, instead of having the piecewise function, choose the right piece for this point 3. Which means 3 is inside this interval. On this interval, we're always using x. Use the formula, use the piece x when we're evaluating this limit. So replace the piecewise function with the piece that's actually relevant for these x's getting close to 3. And once you've replaced this piecewise function with the particular piece, now you can treat this like the other limits that we've encountered. In particular, in this case, this is a polynomial. You find limits of polynomials by evaluating. So you put in 3, and we get this number 3. So that isn't surprising given the graph. This looks to be about height 3 right there. But what's important is this process of when you want to find limits of piecewise functions, you do it by picking the right piece and then just using that piece. However, you have to go about finding the limit of that. Where things are more complicated is if you take the limit where we're switching pieces. So in this case, for the absolute value, that's the limit as x goes to 0. And in this case, the problem is if you're close to 0, if you're to the right of it, if you're to the right of it, you're in this region, so you're using x. But if you are to the left of it, better color. If you're to the left of it, you are less than 0, and you're using minus x. So which piece we use really depends on which side of 0 you're on. So how we'll go about finding the how we'll go about finding this limit is we'll think of this in terms of our one-sided limits. When we talked about one-sided limits, one of the pieces we said was if you want to find a two-sided limit, one way to go about it is check the two sides separately. If you get the same number, that number is the limit you're looking for. If you get different numbers, then the limit doesn't exist. So that's the way that we'll go about this. We'll write down the two one-sided limits, work each of them separately, and then depending on which numbers we get, we draw our conclusion about this two-sided limit. So if we start from the right, the limit as x goes to 0 of the absolute value of x. Here is like this first case here. If you are to the right of 0, we are to the right of 0. No, can even draw. Okay. To the right of 0, we are greater than or equal to 0, so we're using the x piece. So then use that piece when it comes time to find the limit. So again, for piecewise functions, the big thing is depending on which x's you're looking at, use the right piece. And once we choose or identify that to the right of 0, we want to be using the x function, then we can forget it's piecewise and just focus on what would this limit be. We don't worry about where it came from, but just say, if we were handed this, how would we do this? And this is a polynomial in this case, so we can put in 0 and get 0 out. In this case, once we're here and we choose this formula, it doesn't matter that there's a plus here. The limit of x as you go to 0 from the right is the same as the limit of x as you go to 0 from the left, is the same as the two-sided limit. So once you pick the piece, the plus doesn't matter that much anymore. In this case, it doesn't affect that we just find by evaluating. And then we do the same thing on the other side. If we're looking at the limit from the left, well, that's where we're less than 0. So the formula that we're using is minus x. So that's the formula that we use when it comes time to really evaluate the limit. And here again, if this is the limit that we're finding, we can do this by just putting in x equals 0. Minus 0 is still 0. And so 0 is the limit we're looking for. And as the very last part, we look at this work we've done. We checked the two sides. We found that we got 0 in both cases. So then we can say that the two-sided limit is 0 because each individual side gives us 0. And since they match, that number that they match on is the limit we're looking for. Okay. Questions about this, either of these, but especially the second one where we're really using the two sides and looking at them separately. Okay. So to kind of contrast this case where the two sides match up, we'll appeal to an example that we saw earlier where we really just looked at the graph. So this function, f of x equals 3, if you're less than or equal to 0, x squared, if you're greater than 0. And let's find the limit of this as x goes to 0, which is the most complicated point. 0 is where we switch from one formula to the other formula. So that's where the most is going on. And when we did this earlier in the course, we looked at the graph. But here we want to do this without looking at the picture. And the process is really the same as for this absolute value function, just we're going to come to a different conclusion at the end. So if we're looking at the limit as x goes to 0 from the right, what we say is to the right of 0 is this piece. That means we're using x squared. And so that's the formula that I'll actually be looking at when I want to take the limit of this. And once you pick the right formula for the area you're looking at, now just deal with that formula. Again, here the limit as x goes to 0 from the right of x squared. Find by evaluating 0 squared is 0. On the other side, if you're looking at the limit as x goes to 0 from the left, then a similar process. 0 from the left, that is to the left, less than or equal to 0. If that's the region you're in, you're using the constant function 3. So that's the formula that we use. And again, once you pick the formula, just work with that. Since it's a constant, it doesn't go anywhere, and the limit as x goes to 0 of 3 is just this number 3. So now these are the two sides, but what we look at is from the right, we got 0, from the left, we got 3. These are different, rather than the absolute value where we got the same thing on both sides. So that means that the limit doesn't exist. Okay. Questions or clarifications that you'd like about this or either of these problems? Or even sort of more general questions about how piecewise functions might work. Okay. So the main takeaway from all of this piecewise stuff is if you're not at a switching point, just use the formula for the region that you're in. If you are at a switching point, you have to use the two sides separately. And in all these cases, you're picking the right formula, and you have to do whatever you need to do with the formula. It could be that your formula is one of these indeterminate forms. Maybe you have to deal with that. It could be that once you pick the piece, there's an asymptote there. You have to deal with that. In the cases we've seen here, once we pick the piece, we can just find the limit by evaluating. But it doesn't necessarily have to be that. Once you go to these stages where you pick the piece, so all these stages where we've picked the piece, you do whatever you have to do. You're kind of starting your problem over. You think, what do I have to do to find these limits? And if you're lucky, like we were here, it's all just evaluating. But if you're maybe less lucky, you might have to do one of these more complicated kinds of limits. So continuing to expand our repertoire of limits we can take, I want to talk about a different type of function, which are trig functions. And the basic fact is for two functions, sine and cosine, we find those limits by evaluating. So for any number a, The limit as x goes to a of sine is just sine of a, find the limit by evaluating, and the same thing for cosine. The limit as x goes to a of cosine is cosine of a. So given a limit, like say this one, x goes to pi over 3 of sine x, you find that by putting that number pi over 3 into sine, and then you need to figure out what number this is. You can do this with a unit circle, and as a reminder, on every exam, you'll be given a unit circle. So you don't have to remember all of the different values, but you should know how to figure out that this value of sine is the square root of 3 over 2. And looking at the graphs, this fact is not really surprising. So we don't need those anymore. But if we look at sine x, so that's this nice oscillating forever in both directions function. It's nice and smooth. It doesn't have any jumps or holes or asymptotes or things like that. And so this is the kind of function where if you want to know what's happening when you take a limit, it's going to where the function already is. And similarly, if we graph cosine of x, that is the same shape as sine, it's just shifted by pi over 2. And so again, this is nice and smooth. There's no strange limit behavior going on. And so that fact makes sense. What we can also do, or well, what you know is out there, is that there are other trig functions too. Tangent, cotangent, secant, and cosecant. And combining this fact with the limit rule in particular that says if you have the limit of a fraction, you can take the limit of the top and bottom separately. So these other trig functions can also be, we can also find limits by evaluating as long as they're defined. Because these functions are all fractions, they all have a bunch of asymptotes. And so asymptotes are their own thing, but as long as you're not at a point where there's an asymptote, you can find a limit by evaluating. With the justification essentially being, we'll do kind of one limit using limit rules, and then know that this always works, so we can just kind of skip past the limit rule part. So if we want to find the limit of x goes to pi over 4 of tangent of x using these limit rules, well, the first thing is tangent is equal to sine over cosine. The limit rule says, oh, you're taking a limit of a fraction, find the limit of the top and bottom separately. Once you have those, divide the numbers that you get. If you check the unit circle, pi over 4, that's 45 degrees. Sine and cosine are the same. They're both the square root of 2 over 2. And while this looks like a mess, it's the same number divided by itself. And dividing a number by itself is just 1. And what we expected to happen is that 1 is tangent of pi over 4. So really here, the way that we'll handle these problems in the future, or unless you're explicitly told do something with limit rules, is, let's say the limit as x goes to pi over 4 of tangent. There isn't an asymptote at pi over 4. So I know that is just going to be tangent of pi over 4, and that I can evaluate as 1. And so this kind of reasoning would work with any of these other trig functions as long as you're not at an asymptote. So this expands the type of function that we can find by evaluating, not just that these are 6 more functions, but that these limit rules let us combine different types of functions. So for instance, focusing on this one, x sine x is a combination of this polynomial and a trig function, but our limit rules say, find the limit of each of the pieces separately. The limit of x, that's a polynomial, so we can find that by evaluating. Sine, we just said, we can find that limit by evaluating. X at 0 is 0, sine at 0 is also 0, so those multiply to be 0. So not only can we do trig functions and polynomials, but we can do combinations of them. And if you're combining functions where you can find limits by evaluating, you can find the limit by evaluating. Where things are more complicated is sine of x over x. In this case, if you put in x equals 0, we get an indeterminate form, 0 over 0. And so this is one where we don't really know what's going on. We know we have to do something, but what makes this more difficult is with sine of x over x, there's not really any algebra that we can do. There's no factoring, there's no conjugate, there's just not a lot to work with. So what we'll say is we're going to take this limit as a kind of black box. We'll just take it as a given fact and say, if you encounter this limit, just we know its value and can use this. And so this limit of sine x over x is 1. We actually saw an example of this. If you look back in your notes, we did an example where we computed some values of this for x getting close to 0. And we saw from that table that it was actually getting close to 1. You could also graph this, and while the graph will have a hole at 0, it does head up towards 1. And a kind of similar limit that's also indeterminate is cosine x minus 1 over x goes to 0 as x goes to 0. So if you put 0 into this function, cosine of 0 is 1, 1 minus 1 makes the top 0, and also the bottom is 0. And these ones, as long as I can do this kind of quickly, sine x over x, as that fact says, it heads up towards 1. There's a hole there because you can't actually put in 0, but we can see the limit's 1. For cosine of x minus 1, again, we can't put in 0 because we can't divide by 0, but it heads towards height 0 as x gets close to 0. So graphically, we can see that happening. These limits on their own are, I guess, okay, but how we'll actually use them is we'll look at other limits that are indeterminate forms and have some trig functions in them. And if we can do some algebra to make either of these expressions appear, we can say, I know those limits, use 1 or 0 as appropriate, and then if there's some other stuff that I can maybe deal with by evaluating. What I mean by that is let's look at tangent x over x. So this is kind of similar looking, but we don't need to take this as a given. We can figure out what this is using this first limit. So how that can happen is say, well, tangent is sine over cosine. That's just a formula for tangent. Instead of dividing by cosine on the top here, move it to the bottom of the fraction. If we do that, then what we notice is we have sine of x over x appearing inside our function. And that quantity, sine of x over x, is something that we know the limit of. So what we decide to do is break this apart into two pieces. Sine of x over x, which we know how to handle, and something else, which hopefully we can figure out on its own. So once we've broken up into these pieces, our limit rules say you can look at the pieces separately. This piece, sine of x over x, is 1 because we know that that limit is 1. For 1 over cosine x, here we can find this by evaluating. This limit is 1 over, sorry, the pen isn't great on here. This is 1 over cosine of 0. Cosine of 0 is 1. 1 over 1 is 1. And then multiplying these numbers together is 1. So in this case, what's happening is that this is an indeterminate form. If you put in 0 right at the beginning, this is 0 over 0. So indeterminate forms say you need to do some algebra. For trig functions, the algebra is make one of these two limits appear, and we're taking for granted that we know what these limits are. I should mention in the textbook, it gives more explanation for where these limits come from, especially this first one. If you're interested, go check it out. I'm not going to worry about it. We're just going to take them as given. So in this problem, this is an indeterminate limit with trig functions. How we proceed is we make one of these expressions appear. We say, I know what this limit is. In this case, this is 1. And then I have to deal with the other part. But again, this is the kind of thing that we can find by evaluating. Questions about this problem or any of this trig stuff? Okay. So as a very last thing, I don't know if I want to squeeze this in a minute because it's not super long, but I also don't want to rush it. So there's one last example we're going to talk about, which says basically this kind of limit works, even if it's not exactly x. With the example here being sine of 6x over 6x, that also is going to go to 1. Even though it's not literally x inside, if you have the same thing inside sine as in the bottom, that also goes to 1. So I'll more carefully lay this out next time, but we can soup up this fact a little bit to allow for things that aren't exactly x inside there. But then with that, I can stick around if anyone has any more questions. If not, make sure you're keeping up on the daily homework. The thing about daily homework is it seems like it never lets up, but they're small enough to be manageable, And I think it's having to keep up with it daily is better than saving it all for a week later when things aren't as fresh. And in the meantime, you haven't been practicing the material. So if you have questions, I can stick around. If not, I'll see you guys next week.
I have a question.
Back in person.
I have a question, but
Yeah.
it's not about what we talked about.
Okay, so I can pull that back up. Yeah.
No, it's not about what we talked about.
Oh, sorry.
Yeah. Did you get my email that I sent you, Professor?
So we can do this without everyone else in here. So we'll so just stick around until everyone else leaves and then we can answer these questions.
Okay.
Okay.
Come on, Kaylee. There we go.
Okay. Right.